Power Engineer.
I am Bailey Ledet. I was the financial and hardware specialist.
Nicholas Ladd, I was the app software and hardware specialist, and I'm also a power engineer.
Our supervisor is Dr. Pugbies Restrepo. He is the Entry Data Chair and Power Systems Engineer. In a review of our presentation, we'll have the introduction, the system components and trade-off analysis, the design viability and originality of our project, our systems code, the engineering standards and risks, financials, and finally the milestones and data outcomes. SolarSort Automatic Irrigator is a compact water device that controls the water output of a hose faucet based on inputs from the user. It automatically dispenses based on the timers that it gets, and it is powered by solar energy. SolarSort Automatic Irrigator gives multiple plants water by automatically dispensing adjustable amounts of water at intervals set by the user. Using SolarSort Automatic Irrigator over other irrigation systems will result in greater water and energy savings. SolarSort was designed in sections that would isolate potential sources of error. So, for example, we started with the on-device code. That way, once we have that built out, we go forward and add our modules such as our valve and our app, and things like that. Major components of the SolarSort are the logic control device, the electric solenoid valve, the 12V power supply for the solenoid valve. We have a 5-volt control relay, which helps the ability to control the solenoid valve. And for our power system, we have the solar panel and the battery pack.
So, the first system component that we chose was a battery pack and a solar power panel. The solar power panel is 5 volts and 6 watts, and it's used to recharge our power bank. And we chose our power bank instead of like a regular circuit because it was more reliable and it made sure the circuit worked. The next component, which I like to call my MVP component, is the Arduino board because it was the main body of our whole project. It maintains the code and it also powers 2 of our other components, which are the LCD screen and the buttons. And it's, like I said, it has the main code for the device and also the app. And it's also Wi-Fi, so it was able to connect to the cloud and it went along with our app. And our next 2 components, like I said, were powered by the Arduino board. And it was an LCD screen, which allows the user to see a menu and set time intervals. And also the buttons, which allows them to change the time intervals and duration of the transcode we wanted. So our next component was a 5-volt 10-amp relay module, which was used to complete the loop. And so what we did was we had a 12-volt chip to power our solenoid valve. And once the relay was powered by the Arduino board, it closed the coil, which closed the switch and completed the loop to power our valve. And here's the chip I was talking about. It's a 12-volt USB power supply, and you plugged it into your power bank, and that was what powered the valve. And it's rated for 9 or 12 volts, and we had that 12 volts so it could power the valve. And then here's our solenoid valve, which was a 1/4 inch 12-volt DC solenoid valve, and we chose it because it could operate between pressures 0 to 115 psi, and the range for a house spigot is about 45 to 80 psi, and it also gave us the flow rate as well, which was 1.5 GPM at 60 psi, which 60 psi falls kind of in the middle of that range of 45 to 80 psi for the range for us. And then here's our enclosure, which we made sure to focus a lot on this as well, because electricity and water and what mixes those 2 together. So we made sure to choose a waterproof electrical junction box that had certain ratings, and that also was easy to kind of make changes to as well. For example, like drilling to allow our wires to go through it, and so that we can also cut through the material while also maintaining the waterproof aspect of it. And then here is, I kind of explained a little bit the design layout. You have your Arduino board powering your LCD, your Arduino board powering the LCD screen, which is where the user can see how often the plant's going to be watered and how long it's going to be watered for. And then you have your buttons over here, which are also powered by the Arduino board. And then you have your Arduino board going to the relay, and it'll be set off once this pin 10 is powered. It'll close the switch on the other side, and then I couldn't find any like images on the website that I used, so this is your 12-volt chip up here, and it's going in a loop, and then once everything's closed, it's going to power this back down.
So for a trade-off analysis, the first part we had to deal with was the process. Our original plan was to use the Arduino Uno R3 and use a third-party Wi-Fi and Bluetooth module. However, we decided to just go and use the Arduino Uno R4 Wi-Fi as it had Wi-Fi Bluetooth integrated and as well as more reliable than the plug-in module. Unfortunately, it slightly increased the component cost, but we felt that was worth it. Another trade-off we had to make was with our housing. We decided to use a pre-made waterproof housing instead of what we originally intended to do, which was a 3D printed housing. This gives us greater strength and reliability, and when moving to manufacturing, it removes the possibility of delays due to indirect printing, which, if you know anything about printers, it can happen just out of nowhere. Unfortunately, it significantly increases the component cost, but since we're reducing delay and we have a physical housing that's ready to go, we think it's worth it. So for our overall design trade-off analysis, the negatives are that it's dependent on solar power, so it needs to have the sun maybe in a window if you want to put it inside, but then you have to worry about the hose splitting as well. So without modifications, you're using compression. When you install it, you also have to take care not to obstruct the panel, whether that be by not if it's going to get easier to do. Positives of this design are that it is self-sufficient, as it has solar power to power completely. There's no external power source, and there's no need to refill the water reservoir as it's constantly pulling from the utility. For our overall system flowchart, we start with two inputs: the interval timer, which determines how often the system waters, and over here, this is the dispensation timer, which determines how long the device will dispense for, which is holding it up. These inputs go to the Arduino processor, which then immediately on startup begins to check if the time elapsed is equal to the value of the dispensing timer. If it is, it then tries to dispense on the interval timer. Once the interval timer value is equal to the time that's elapsed, we can go to the dispensing timer, which is initiated, and at the same time we open the valve to dispense water. The valve then remains open while the dispensing timer runs. And once the dispensing timer is up, we close the valve, which stops the water flowing, and then we go and reset all values to the original thing and loop it again.
Section of society and impactful. So in 2022, the global irrigation automation market was evaluated at $4.2 billion. It is projected in 2027 to be at about $9.2 billion. And it was seen that 20% of American homes already have a watering system of some sort. Our system is designed to serve a wide range of customers from a small scale of home users to a larger scale of farmers with plant nurseries, but really anyone who has a need to water plants and has access to a water spigot, it will work. And then our system is efficient and convenient, ensuring optimal growth conditions with minimal effort on the customer's side. Our economic viability, our system saves time, energy, and water for the users. And then on the larger scale of the farmers, they can reduce water usage, increase crop yields with the consistent watering schedules, and then it has lower labor costs as it will remove the need for manual watering $60. It connects to an outdoor water spigot, comes with a smartphone app. It has timers that are adjustable. It has weather-based watering capabilities. It runs on disposable batteries, and then you also need access to a standard electrical outlet that's 120 volts to plug your device in if you want Wi-Fi. And then there were a few others, such as the downfield watering system, but this is more for indoor plants, smaller scale, and you need wall power or batteries. Okay. Our concept, as we just saw, is not necessarily new, but we added features that do make it stand out. So we have the 2 buttons that allow you to set your different timers. We have an app, our smartphone app allows you to see the countdown, a live countdown timer of when the next watering cycle will begin. And we also do have a switch on it where you can override the timer and just turn your plant watering system on or off at any given time from anywhere, as long as your system is at home and connected to your Wi-Fi. And then we have solar power. Our solar power makes our system greener, which reduces overall energy consumption and saves money. Because we have solar power, it's not dependent on another power source, and this eliminates users changing out batteries as well as needing access to an outlet.
For the on-device code, the section that the user will see pretty much all the time, as it's always displayed, is the main menu. The main menu is created by simply having the LCD print text that we've pre-positioned, and then we'll stick in the timer inputs as we need to. So, for example, right here, we have watering every, in this case, it's 1 day, 5 hours, and 4 minutes, or 1 hour and 2 minutes. So that system will always be present. But the main menu is programmed to update whenever a difference in the current and previous timer settings is detected. That's something that we added so that when the user goes through and changes their timer, it'll automatically refresh the main menu and they'll see the most recent information. We also take advantage of that behavior once we get to the watering operation, as we need that to cure our watering usage. For the timer inputs, a series of menus are displayed for each timer, allowing the user to cycle through allowed values using the button module. And these menus are prompted from the button module to begin with. Users are prompted for each section of their timer input, for example, days and hours, and the buttons are programmed to increase and decrease value. We've set reasonable input limits for these values. So, for example, bring in hours, you can only go between 0 and 23. And to prevent errors, which we did run into at some point during testing by accident. If you end up with a total timer value of 0, the device will just go in infinite loop and have to go through and strip the memory. Not good. So we prevented that, and it now checks and sends the user back to the beginning if they put all zeros for everything. For our timer conversions, it's just a simple multiplication to take all of the timer values, like days would be converted, hours are converted minutes, and we all get that into milliseconds because the device keeps time in milliseconds from the moment it starts up. So using that as a compare, we can keep track of how much time has passed. And the main part of our code as far as functionality is concerned is the watering operation. So it keeps track of how much time has passed since startup by using the millis command. And once enough time has passed, the solar valve is opened according to the duration of time. So right here, you can see how we're using millis. Notice it's just a generic command it's always keeping track of. So we compare the total millis value to the start millis, which is the time that's already happened from the moment watering operation is called, to the total timer water millis that we showed earlier. And that will hold the valve open for as long as we need to, at which point, as we mentioned earlier, pin 10 is set to low, which opens the relay, which in turn opens the valve, everything shuts off, and everything is reset by updating the screen.
So one of the main features of the app is that it's a timer, so the person can see it counting down. So like say they set it for a day, they can see it count down until it reaches 0 and then it'll reset. And the code over here, basically it just checks if a minute has gone by. With a minute conversion, it kind of runs off of Jacob's code a little bit, where it takes that millis and then it converts it into a minute, and then it checks to see if a minute has passed by. If a minute has passed by, it'll subtract the minute from the timer app, and then this hours kind of just goes off the minutes as well. See, you can check to see if 60 minutes have gone by, then it's subtract an hour, and then 24 hours have gone by, and it's subtract a day. And it kind of each, if statement just goes off the minutes. And then another feature is the user is able to, if they want to water their plants extra, they are able to switch on a button and it'll automatically start dispensing until the user switches that off. But it will reset the timer. And so say they have it set for like 24 hours and they switch on like 22 hours in with 2 hours left. Then it'll reset back to 24 hours. And so this code over here, so on user water plant change function, when that switches on, this function will run, and it will run until it switches off, and then it will reset the timer. And this over here is the display of our app. And then here's a video demonstration. So we may or may not have set for a minute to run.
And then there's this small amount of time to come forward.
And then it goes back to the main, and you see it resets. So some of the engineering standards we went off of, one of them was NEC Article 675, which talked about electrically driven or controlled irrigation machines, which provided some information on like grounding for controls and waterproofing as well. NEC Article 110.28 also enclosure types, so it gave us the enclosure ratings like rainproof, waterproof, and other descriptions of what kind of enclosure we needed. And finally, we used NEC Article 690, which provided information on solar voltaic systems for our solar panel and information on that as well as what we needed to do. So some potential risks, Jacob and I are mainly power engineers, as we stated in the beginning, so a lot of our focus is on power. And we did app coding and device coding, so we kind of had to get familiar and do some research on that, especially with the Arduino. We didn't have much experience with that, so we had to do some research. And it places, like I said earlier as well, another risk was it places electrical components near water, which can be very dangerous. And then finally, when we ordered the components, we didn't know if they were going to be effective or not, like if they were going to work, so we had to test them. And if they didn't work, then we would have to order new ones and wait, but thankfully, all of our components worked.
On the financial side, our parts cost, so all of the parts that Jacob and Nick talked about, plus a few other pieces, our total came out to $158.31 to build all the device. Our budget, we had a $200 budget funded by UNL, $158.31 from that, and we had a remaining balance of $41.69. Our fixed cost is took into the salaries of 3 of us, Dr. Parvies, our supervisor, our leasing, accounting, and payroll, and then our marketing, which we're doing a marketing on the social media side. So that came out to $17,325 a month. Our break-even analysis, we use that fixed cost per month, our variable cost per unit, and then for our selling price we took our variable cost and put that up 35%. So we get our selling price came out to $213.99. And our break-even point has us at selling about 311.15, so 312 units per month. This is our break-even point analysis graph. You can see at the black dot, that's our break-even point, that's the 312 units per month, which comes out to be $66.5 thousand a month in revenue. That to reach our break-even in a year, we'll either need to sell 312 units a month or 3,744 units a year. 2021 design milestones. We did this for both classes. In senior design 1, we went through topic selection. We did 3 presentations within just our class and Dr. Harvey's, where we were able to improve our design, work with things, do research. We had a paper and our final proposal. Then we were able to use feedback from judges, take it into this semester, and build a better product. Senior design 2, we had coding, construction, we had app development, energy and power, we have documentation, and then our final presentation today. And our papers will be due on December 6th. AVET outcomes, we have all 7 listed after this, but just shorten it because of time. We're just going to cover AVET outcomes 2 and 4. AVET outcomes 2 is our design. So our solar soap system is a smart way to water your plants. It has a connection straight to a water spigot, it has button controls, an LCD screen, it limits the amount of water dispensed. It has 2 user inputs that we saw, and so our design will lead to water and energy conservation, as well as receiving the correct amount of water for your plants. AVET outcome 4 is ethics. We ensure that our system operates safely, efficiently, and without harm to the environment. Throughout designing, we considered how our system would contribute to water conservation and plant health. Our main goal was to increase water savings and energy savings while also creating a safe device that would combine both electricity and water, and we performed multiple tests throughout the semester to ensure that our device does work properly and safely. These are just 1 through 7. We will not review each of them. And then to say thank you, we would like to thank Dr. Harvey's just for the guidance and believing in us as we went through this semester, guiding our academic achievements. We'd like to thank the University of New Orleans for the funding and the testing equipment necessary. We'd like to thank our friends and family who came out today to support us, and then also to the judges who took time out of their day to create a platform for us to present our device on. We'll go through question and answers, and then we'll do a live demonstration outside.
What's your committee? Let me start this off.
So, I was looking at your AVET going through, so you mentioned that you make sure that no plant is not receiving access, or at least receiving the minimum amount of water. How do you make sure that, that being done?
So since it's we have that our valve dispenses 1.5 gallons per minute, since it's for gardens, we would be able to say that the user can select how much water your plants would receive.
It's something that you pre-define manually at the time, or that these are the types of plant that would require maybe less water for less duration. So that's something you pre-define manually. Is that correct?
How much water is dispensed?
Yeah.
So that's just dependent on our spec sheet from our valve.
And also the amount dispensed can change based on the type of hose the user decides to use. For example, if they use a drip line that has a bunch of little holes in it, the amount of water is going to be much different. So really that's something that they need to figure out, unless we would go through and choose out a drip line and things like that. If we did that, then we could do it. But right now it's something that they would figure out based on the time.
On our valve, we have a connector, so you can connect any type. We have 2 adapters, one to connect straight to your faucet. The other adapter is connected to any type of hose or water spigot. You can just run to the store and grab it. So it really depends on if you want 1.5 gallons, you would set your timer for a minute. If you want your plants to get 3 gallons, you'd set it to 2 minutes, so the user can change how many gallons their plants would receive.
So, you consider something like soil moisture, that could be one of the input that you could, take into account. That could maybe try to automate this timing thing. Is that something you take as an input, like soil moisture?
So soil moisture, and another similar thing that we considered was rain detection. Just, so if it rains, we wouldn't water. We thought about that, and for soil moisture, it's not really reliable because what we're doing is something that's more of a larger scale. It's designed to control the hose input. So if we probe a part of the ground that happens to be wet, but the rest of the garden is dry, then the watering won't be done properly because we're taking that input. The same thing is with the rain sensor. Perhaps there's a sensor that would work better for what we did, but the one that we ordered It ended up having too many false positives because of the way that the detection worked. Is pretty much if any water at all was just on the sensor, it would say, okay, well, the sensor's on now. And we don't have a way to tell between how much rain, let's say it sprinkles for like 5 minutes or whatever. That's not enough to water plants, but our device couldn't tell the difference. So we decided not to include any moisture sensor in your rain or anything like that, at least at the moment.
Okay, question?
So, is the user only allowed to program the frequency of watering and that's it?
No, so they program the frequency of watering and also the amount of time that the valve will stay open for.
Okay, so basically user can, if I want to set it to water at 2 different points of the day that already the business, let's say I want it to water at 6 a.m. and at noon, that's not something I can do, can I? Because it's not gonna happen again at the same time, it's gonna be more hours until it happens again between when the first interval of one happens, the second one. So, because if you, like, I feel like you should program it as being able to program start and stop intervals, so that people can do different intervals at different times, because as far as I'm aware of a lot of different plants, people are gonna be able to do something like water in the morning and afternoon, but the time between morning and afternoon is gonna be the same as the time between afternoon and the next morning again. So that means they can't just program out a frequency and a duration.
I understand what you're saying.
Is it hard to modify your?
I think it should be easy to
that's-
change some code to do that.
Yeah,
That's right.
it's definitely achievable through software. We would have to think about how we would handle, because the time system would have to change at that point. But it's totally possible if we want that.
Yeah.
But that's kind of why I added that switch button, so if they wanted to go in at a certain time.
Yeah, but we're telling people to program, so they don't have to do that.
Okay, other question? Any other question? Okay, sorry.
Did you use the external plug? The one with the external plug for usually the minute and
External plug for your.
No. So all timekeeping is done on the device itself using the millis command, which is just the amount of time it's been on for. So there, as far as the device is concerned, it has no reference to what time it is at all. It's simply just how much time has passed from start up. Yeah.
Okay.
this is my feedback. If you would like to run a relay, start a relay with the micro, there's a problem. Just use the buffer between the micro and relay. The buffer is the buffer.
Okay. All right, this is wonderful. You did very good. Let's give them a round of applause.